This is take 5. This is the one. Okay, climate change part 2. Wanted to make sure that we were going to have enough time on this. So questions that we're answering in this second part of today's lecture: how do we know that the climate is changing, and how do we know that humans are driving climate change? So one of the major arguments about climate change is that the climate has always changed, which is true. Okay, so yes, the climate has always changed. Yes, there are natural cycles that govern temporal climate changes. So these could be seasonal, yearly, decadal, or multi-century. So if we think of seasonal, we can look at this graph right here. This is carbon dioxide daily and weekly means, so daily and weekly averages at Mauna Loa, which is an observatory out in Hawaii, and it's observing carbon dioxide concentrations in the atmosphere. Notice that it varies by season, right? So it looks like we've got a peak in May, and then maybe another peak in March, and then bottoms out around September. With this, if you think about land mass in the world, the northern hemisphere has more land mass. Therefore, the northern hemisphere has more trees, and therefore, during northern hemisphere spring and summer, so June, July, August, September, October, you have that bottoming out of CO2 because you have more photosynthesis happening. Likewise, in northern hemisphere winter, you have the trees in the southern hemisphere that are leafed out, but there's not as many of them because there's not as much land mass in the southern hemisphere. And so because of that, you see CO2 spikes in northern hemisphere winter or southern hemisphere summer. Okay, yearly. So with yearly, we have El Nino. So here's our yearly El Nino cycles. Notice it's not necessarily every year that you have an El Nino or La Nina, but it does change yearly, or about pretty much yearly. You do have an El Nino about every 5 to 7 years. Remember, El Nino is just a warming of the equatorial Pacific Ocean. Okay, moving on. We've got multi-century variability. So these are Milankovitch cycles. There is an extra video on the Haiku page if you are super interested in this. But this is essentially what causes ice ages. So this is based on eccentricity and axial tilt. So eccentricity just means like, is the orbit circular or is it more elliptical? So that orbit changes. And then axial tilt is how much wobble the Earth's axis has. So when the natural variability is the most oblong or most eccentric, you end up with less direct sunlight at a less direct angle making it to the Earth, and therefore you end up with colder temperatures and ice ages happening. So that has to do with Earth's orbit around the sun. This happens about every 24,000 years, and you can predict ice ages based on the Milankovitch cycles. It's interesting stuff. I recommend checking out the other video if you are interested in it. Good stuff. Okay, another thing that's going to be linked on Haiku is thousands of years of climate data. I'm going to show it to you really quick, maybe. And keep in mind the dotted line shows proxy data and the solid line shows recorded data. So if I click on this, will it work? Oh, it does. Okay, so this is called XKCD. It's a webcomic. It's funny. But this is a timeline of Earth's average temperature since the last ice age. The temperature average 0 is based on the 1961 to 1990 average, and it's graphing the anomaly, okay? So notice, like, it has a whole timeline. It's very long. We don't have time in this video to go through every single thing. But it's talking about how the Earth's climate has changed. So notice we start way cold in an ice age, and then we start to warm up with the dotted line. We cross over to normal. We stick around normal for a while, and then we get all the way down to here. The black line is when we have started recording data, and we start to see this like exponential growth curve. So check that out. It's linked on Haiku. It's pretty interesting, I think. I think it's worth it. Okay, so that shows proxy data and recorded data. So what is proxy data? Ooh, sorry. Okay, proxy data is using other kinds of data to estimate what global climate was like. So some proxy data that we can look at, you can look at tree rings to look at how wet or dry a season was. You can look at glacial cores or ice cores to see how much CO2 was in the atmosphere. You can look at pollen, which is super interesting, to look at previous climate. And you can also look at like seafloor sediments and coral. And I forget what you can look at in caves. This first thing here, this is not proxy data. This is old ship data. It is recorded data, right? It's recorded weather data. There's actually a citizen science initiative where you can go on and you can record old ship data from old ship logs so they can have a digital copy of it. So if you're interested in citizen science, that is linked on Haiku as well. It says, I think it's called Old Weather. Okay, so climate models. So when we talk about the models, what are we talking about? We build climate models in order to predict how the atmosphere will behave. So we have weather models and we have climate models. So weather models are what you see when we are talking about like short-term forecasting, okay? Climate models are talking about like what direction is the climate going. My question is, how do we test our climate model, and why are climate models more accurate than weather models? So what you have is a grid on Earth, like of Earth, essentially, and you can plug in actual data that you have and data trends, and based on those trends, you can see where the projections go for what future data will look like. The reason why climate models are more accurate than weather models are because weather models have to try to figure out what every single particle in the atmosphere is going to do, and there's more variability in that, and there's more chance for like a change in that, whereas a climate model is trying to predict which way the atmosphere is like headed. Okay, so for example, let me see if I can draw this really quick. So if we have a weather model, let's say my weather model, I'm going to graph like temperature, okay? And I'm going to start with like Monday, Tuesday, Wednesday, Thursday, Friday. And I'm going to say I predict these different temperatures. Okay, so that would be my weather model. Okay, my climate model would say I predict that as the seasons change, the temperature is going to increase. Okay, so the weather model is trying to predict like exactly every day. The climate model is like increasing just over time. Okay. So how do we know that our models are good? So what we have is we take our observed data, okay, and we try to match that against what our models have, okay? So if I put into my model just, oh, and this is also like, how do we know that humans are causing this climate change, okay? So I can put in natural forcing. So those are like natural changes in Earth's climate. So things that we would expect with Milankovitch cycles, with like decadal cycles, changes that we would expect. So back here around 1850, it matches okay. It's not great, but this is natural forcing only, so the observations are in red. The blue is models, okay? So it like kind of matches, but then when we get to about 1975, it really diverges. Now, let's say we want to have just our anthropogenic forcing. So we're saying like none of this is natural, this is only humans, okay? So notice it looks pretty noisy back here, and it stays okay, but there's like some major difference here, and it's our observations are higher than what the model would still suggest, okay? And this is just anthropogenic forcing. But if we have our natural and anthropogenic forcing, and we put those two things together, so saying like the climate is changing because of different cycles, and the climate is changing because humans are emitting CO2, so both of those things, and we put those both into our model, notice it matches our observations and results match almost like very, very well, okay? So that is kind of how we test our models, and that's how we then plug them in to like project into the future what we expect. You will notice a lot of times with climate modeling, especially when we're talking about climate change, we talk about a business as usual scenario, a medium emission scenario, and a low emission scenario. So we change that anthropogenic forcing to get different outcomes based on human behavior. Okay, we'll talk more about outcomes and what else is going to happen, or predictions, I guess, in the next class. Global temperature anomaly, we're running out of time. So notice that in 1880, we were below the average, the 100-year average between 1901 and 2000, and then about 1980, every year we've been above average. So this shows us, things are changing. This is also showing you some other graphs. I'm going to put this up so you can look at it. But this is looking at sea level change, greenhouse gas, CO2 emissions, sea and ocean, sea and land temperature anomaly. So all these slides are going to be up on Haiku for you, okay? Okay, so next time we're talking about impacts and mitigation and adaptation. It's going to be more hopeful. So the last thing that you have to do for class today is to address 4 climate change myths, which hopefully I can show you really quick. This is all in Drive, and you are going to need to go and then make a copy of it in order to be able to edit it because it's view only for you. But you can go on, you're going to pick 4 myths to explore, and then research the science behind each myth and provide a counter argument that includes sources. Please cite your sources. Don't copy and paste. So there are 24 myths. They range from sea level rise is exaggerated, to it's freaking cold outside, to Al Gore's wrong, to ocean acidification isn't serious, to climate sensitivity is low. So it's a bunch of claims that people that disagree with climate change have made in the past, and pick 4 of them, research them, give me a counter argument. Office hours 1 to 2 on Wednesday and Thursday. Come by, say hi. I hope that you are all well. I hope that you are washing your hands. I will see you. Bye, guys.